On September 1st, 1983, Korean Airlines Flight 007 departed as planned from New York's JFK Airport en route to Seoul via Anchorage. It had 269 people on board, including passengers and crew members. However, what should have been a routine international flight turned into a tragic incident that shocked the world. Due to a navigational error by the flight crew, its course deviated from its intended flight path right after departure. Instead of heading towards Seoul, the Boeing 747 strayed toward the Kamchatka Peninsula, eventually entering Soviet airspace. As warnings from Soviet air defense systems were not noticed by the crew, the plane continued to fly even deeper into Soviet airspace. This prompted the Soviet military to send fighter jets to intercept it. Tragically, Soviet fighter jets shot down the aircraft, causing it to crash into the Sea of Japan. All 269 people on board were killed. This incident highlights the need for aviation radio navigation, as the crew was unable to notice and correct the wrong course via visual indications. Navigation is commonly defined as the science of determining the position of a vehicle and guiding it to a specific destination. Navigation aids are found in the airspace, on land, in the sea, or even in outer space. In the aviation context, we are interested in aircraft navigation. Of the various navigation technologies available, some are self-contained, such as the inertial reference system. Most methods are, however, based on external references, such as the Earth's magnetic field or radio waves. A radio wave is defined as an electromagnetic wave within the broad frequency spectrum from 3 Hz to 300 GHz. In comparison, the visual light spectrum and gamma radiation are many orders of magnitude higher in frequency. Prevalent navigation aids are ground-based stations, so-called beacons, which emit these waves. After a radio wave reaches the aircraft, the incident angle can be determined. This incident angle is also referred to as bearing and narrows down the relative position of the aircraft toward the radio station. In this example, we now know that the airplane is somewhere located on the blue line. The incident angle measured from north of the aircraft is referred to as relative bearing. An absolute bearing, on the other hand, refers to an angle relative to magnetic north. To reach a certain goal position, the aircraft can head toward one station after the other along the way. This is the simplest but also most inefficient method, as the path is usually not optimal. To plan a better route, the exact position of the aircraft can be determined by using the bearing of several radio stations for triangulation. Note that in this example, 3 stations with bearings are shown. However, 2 bearings would already suffice to determine the location in the horizontal plane. So far, a generalized radio station was assumed. In fact, there are different types of radio beacons, each having its own icon. They typically have a range of up to 370 kilometers. First, we will have a look at the oldest type, the Non-Directional Beacon, in short NDB. NDBs were first developed in the early 1900s and were initially used for maritime navigation. However, as aviation technology advanced, NDBs became an essential component of the aviation radio navigation system. As the name implies, they broadcast a continuous signal omnidirectionally, typically in the low to mid-range radio frequencies. Historically, the bearing information was obtained by manually rotating a directional loop antenna. Today, the process is automatic and referred to as automatic direction finding, in short ADF. To obtain the bearing information, the pilot sets the ADF receiver, displayed on the left, to ADF mode and enters the frequency of the desired NDB. Afterwards, the ADF receiver needle points toward the NDB station. Non-directional beacons are prevalent due to their simplicity and cost-effectiveness. Problematic, on the other hand, is the low accuracy of the supplied bearing information with only 5 to 10 degrees. Furthermore, the signals are susceptible to a range of adverse effects, like multipath due to mountains and atmospheric effects caused, for example, by thunderstorms. Therefore, NDB stations are gradually decommissioned and will be phased out by 2030 in the United States. In contrast to the non-directional NDB stations are the directional VOR stations. With VOR stations, bearings can be estimated with higher accuracy and lower vulnerability to atmospheric effects. VOR stands for Very High Frequency Omnidirectional Range. Until the beginning of the 21st century, VOR stations were the standard air navigational system. Similarly to the NDB, they continuously send out a non-directional signal. This signal is represented in white in the animation. Additionally, a directional signal is emitted, which changes its phase relative to the continuous signal depending on the radial of the beacon. In the animation, the red cone represents the directional signal, which rotates around the beacon like the light signal of a lighthouse. The graph on the right-hand side depicts the phase relation between the emitted signals. Let's have a look at individual examples. If the aircraft is located exactly north of the VOR station, there is no phase shift between the received signals. They overlap exactly. If the airplane is located east of the VOR station, it will observe a 90-degree phase shift between both signals. Similarly, there is a 180-degree phase shift in the south. The determination of the bearing is a little different compared to NDBs. First, the radial of the VOR station to the aircraft is determined, which is equivalent to the observed phase shift. Based on this information, the bearing can be calculated. VOR stations are often paired with other air navigational systems, for example TACAN or DME. Next, let's have a look at the conjunction of a VOR beacon with DME. DME, the abbreviation for distance measurement equipment, is essentially a transponder ground station for measuring the signal propagation delay. First, the aircraft sends out a signal. Immediately after reception, the transponder of the DME station sends a response signal. By measuring the time delay between the sent and received signal, the time of flight can be determined. This enables the calculation of the total distance between aircraft and DME station, called slant range. Usually the horizontal range is of interest. If the aircraft is located far away from the DME transponder, the slant range can be assumed to equal the horizontal range. Only a negligible error is made because the horizontal range is far larger than the aircraft height. However, with decreasing horizontal range, this error increases. With the DME VOR station, not only the bearing information can be obtained, but also the distance. By adding this constraint, the aircraft can be pinpointed on the bearing line. Compared to NDBs, VOR beacons provide higher accuracy bearings, are less susceptible to atmospheric effects, and are more versatile due to additional TACAN or DME stations. However, they are still ground-based beacons. An infrastructure is required, and they are not available overseas. The dependence on ground-based stations can be reduced by means of satellite navigation. This has the added benefit of global coverage and reduced infrastructure costs. While beacon navigation is based on triangulation, the principle behind satellite navigation is trilateration. By determining the signal time of flight, the distance between aircraft and satellite can be calculated. Note that one satellite is not sufficient to obtain the position. Using the distance as radius, the aircraft can be positioned anywhere on the circle around the satellite. In the horizontal plane, 3 satellites are sufficient to obtain the exact position of the aircraft. Note that in 3D space, at least 4 satellites are required. Unfortunately, the satellite signals are distorted due to atmospheric irregularities, especially due to disturbances caused by the ionosphere. The result is a significant loss of accuracy and reliability, which renders standard satellite navigation impractical for aviation. The solution to this problem is called augmentation. There are 2 different variants: SBAS, short for space-based augmentation, and GBAS, which stands for ground-based augmentation. In SBAS, specialized ground stations receive the distorted satellite signals and calculate the precision error. This error correction information is then communicated back to the satellite, which adjusts its signals based on the received information. With SBAS, an accuracy of 3 meters can be attained. Even this improved accuracy is not sufficient for landing and approaching maneuvers, which is why GBAS is used. As with SBAS, the GBAS station calculates the precision error, but instead of transmitting it back to the satellite, it communicates directly with the aircrafts nearby. By using the satellite signal and the correction information, the aircraft is able to update its location with an accuracy of less than 1 meter. GBAS is most commonly used near airports because it has a much shorter range than SBAS. With the newly obtained information about radio aviation navigation, let's have another look at the reason for the divergence of Korean Airlines Flight 007's route. At this time, satellite navigation was not available for civilian aviation. The crew was instructed to head toward the FORTAC station at Bethel and to switch to the inertial navigation system afterwards in order to follow a pre-programmed route, as there are no radio beacons overseas. However, the aircraft missed Bethel and already deviated so far from the intended course that the inertial navigation system did not follow the planned route. The crew was unaware of this fact, and thus they continued the wrong path for more than 5 hours. Fortunately, flying has since then become safer than ever before. A major contributing factor is the advancement of aviation radio navigation, in particular GNSS augmentation. This video was produced as part of the Avionik Devices seminar at the University of Würzburg. Thank you for watching.